So up until now, we're used to thinking of space and time as independent quantities. So that is distance and time is time. We know that those two quantities are linked by the speed. So the faster we travel, the more distance we cover in less time. And as we study relativity further, we'll find that the two concepts, that distance and time, are much more closely linked than we realized. So we will refer to these two quantities as one thing, which is space-time. So rather than talk about an object's position, we will now talk about that object's position and include the time that it was at that position. And that's all that space-time is. So our three-dimensional position vector, our x, y, z, now becomes the four-dimensional vector, which is x, y, z, and t for the time. So every single point in space is now defined as a point at a time. And we represent this space-time using a coordinate system that's very much like our Cartesian system, with a couple of small differences. And the first of those is that on this diagram we put our time on the y-axis. Because it is difficult, if not somewhat impossible, to clearly represent a four-dimensional vector on a two-dimensional page, I will limit all the discussions to one-dimensional movement, so as we've done previously. So our space-time diagram, for the rest of this topic, our coordinate system, will have our distance in the x direction on the x-axis. In this diagram, we call the line that describes the motion of an object through space and time as its world line. So if we have a look at three objects, we have a man, and this diagram is from the man's viewpoint. So this diagram is representing the man's reference frame. And from his viewpoint, he's stationary. Then we have a photon of light, which is moving at its constant speed of c, and we have a rocket ship, which is travelling past the man at some velocity v, so quite a high velocity, relative velocity v. On our space-time diagram, our man is stationary. It's his perspective, he's not moving. So he's not moving through space, but he is moving through time. So his world line is a straight vertical line. For him, time is passing, but his position is not changing. Our rocket is moving with some velocity v. So at time t equals 0, the rocket is in the same position as the man, but after 1 second, the rocket has moved at whatever velocity it's travelling. So it is now slightly further away from the man. So its x position has changed. So its world line, the world line of the rocket, is this line with this gradient. And if the speed of the rocket were to increase, then it would move a further distance in that 1 second. And the final object we have is our photon, our light beam. So the speed of our light is the limit of the speed of things can travel. And so it's going a significantly further distance per each time interval. So if we have a look at the gradients of this, we can see that the gradient of our velocity is equal to the time divided by x, rise over run. And the gradient of our time is equal to 1 second divided by 3 times 10 to the 8 meters. So that's a very small gradient. So for this reason, and also for other reasons which we will see in the next few slides, we change the y-axis of our diagram, and we say that the y-axis is now equal to c times t. So that's the speed of light times time. And that means our y-axis is in meters and our x-axis is still also in meters. So with this new set of axes, the world line of our man still doesn't change. He's not moving through space, he's just moving through time, so he still has a vertical line. The gradient of an object with velocity v is now equal to ct divided by x, and that means that the gradient of our speed of light is equal to 1. And so that puts our speed of light, the fastest we can move, as a reference point in the middle of our axes. And that makes things much easier for us to see, and it also makes things much more convenient, as we'll see later on. And that means that our object with gradient v plus and v, and in the next video, we'll start to look at the concept of simultaneity using the space-time diagrams.